Hey everyone. Recently, I've been working with motion matching inside of Unreal Engine 5.3. It's still experimental, but it is in a much better state than it has been in previous engine versions. And I've created a basic strafing setup using some of the animations from the Lyra starter project that is fully driven by motion matching. Every pose that you're seeing here is coming out of a motion matching node, and this system is not perfect. This system is not polished, and definitely isn't feature complete. There is no turn in place or anything like that. You can only jog, and we can play a fall animation when we're in the air, but there's no active jump or recovery animation being played. The unarmed animations from the Lyra starter project aren't the cleanest animations either. I don't think Epic spent as much time polishing them, as there are some issues with the root motion that do become visible, especially in some of the pivots, such as the pivot backwards to forwards animation, where we see some foot sliding occur during the transition, and that's, I believe, due to improper root placement in the pivot animation. This is not the greatest motion matching system in the world. That said, I did put it together somewhere between 3 and 5 hours, so there's a lot of room for optimization and improvements, but I just wanted to show you guys what can be done with a minimal amount of effort using motion matching, and so that's what this video is going to be about. I want to walk everyone through the process that I went through as I created this locomotion system, and I'll do my best to explain the basic principles of motion matching inside of Unreal Engine as I go. Now, before we begin, I have started a Patreon for the channel, and it is linked in the description. For $10 a month, you can gain access to the project files for tutorial series that I put up on this channel. This includes the project files for the ongoing Advanced Character Locomotion tutorial series, as well as the project files for this basic motion matching setup. And I plan to continue putting more project files up onto my Patreon for you guys to access as well. So if you would like to support me and gain access to the project files, definitely go give that a look. Now let's get back to the video. First off, what is motion matching? Well, let's take a look at some of the setup here, and I think that will aid me in my explanation. I'm going to make my way into the animation blueprint, and I built this off of the default animation blueprint inside of the third-person template, as that was just a bit easier. I wasn't trying to make something complete. This was more of an experiment, so I started from that rather than starting from scratch. I have a relatively simple state machine here with 4 distinct states, but if I click into one of them, there is no sequence player or sequence evaluator. Instead, there's a motion matching node. And instead of taking in an animation sequence, it takes in something called a motion database, as well as a trajectory. Let's look at this database asset and see what's inside. There are 4 animations listed here in that cycle database: a jog forward, backward, left, and right. What motion matching is doing is it's looking at the animations inside of this database here, and it is evaluating them with a few different metrics, primarily a trajectory and a pose. We can see the trajectory here, these 4 points along the ground. There's 1 evaluated point in the past, 1 at the present, and then 2 in the future. It is also evaluating the pose at these 3 green points that we see here. The left foot, the right foot, and an upper spine bone is how I've set this up. And these are set up in the motion database configuration file assigned to this motion database asset. I'll cover this in more detail later, but what this does is it assigns metrics for the motion database to measure inside of the animations that are put into the database. In this case, it's a trajectory and a pose. So we have a database with multiple animations, and this database is being fed into a motion matching node along with a trajectory. And previously in this graph, we have a pose history node, which is tracking the 3 same bones that we're evaluating. Well, this pose history is keeping track of a pose over time. And we're feeding in this variable that is a trajectory. And this motion matching node evaluates all of the animations in the database and chooses the pose for a frame that most closely matches the previous frame's pose and the input trajectory. If I play again, I'm going to open the command window. The command, I guess it's not really a window, more of a line. Probably has a proper name that I know, but just am forgetting currently, but I'm opening it with the tilde key. And I'm going to type trajectory. Now, you won't have access to motion matching or this trajectory command by default. There are some plugins that you'll need to enable before you build a motion matching system. I'll go over that once we get to the setup. But for now, I just want to do my best to explain the underlying principles here. So, oops, I entered the command, but I did not give it a value. We need to give this character trajectory.debug command a value of 1 to turn it on. And now we can look at the trajectory that is being predicted for this character. I'll go over how we can get this set up later, but for now, this is what is getting fed into that motion matching node. And what the motion matching node does is it compares the input trajectory to the trajectory of the animation and the input pose from the previous frame to the poses in the animation. And it finds a frame in the animation where the trajectory and the pose most closely matches what is getting input. And so it is not restricted to playing animations in sequence one frame to the next. Every animation in the database is evaluated every frame, and it tries to find the optimal pose. That's why, while I cycle, I can switch from jogging forward to jogging right. I don't need to provide any logic for switching between the forward animation and the rightward animation. It figures it out because the trajectory has changed. Now, I do have some separate motion databases. One for cycle, one for pivot, one for start, and one for stop. And that's because I did put together, as you saw, a bit of a state machine structure. And that is because in certain situations with limited animation coverage, the motion matching system doesn't always choose the pose that we want it to. We are turning away some level of control when it comes to decision making to the computer. We're not defining the logic as clearly as we would previously, which means that we do lose some control, but we do gain simplicity, and in a lot of cases we do gain a more natural looking motion with motion matching. But I do want to demonstrate something here. I'm going to right click and create a motion matching node here. Now, you do not need to follow along. We will get to the setup portion of this video, but I do want to demonstrate what happens when we put all of our animations into a single database. So I'll go ahead and copy this cycle database. And I'm going to delete out all the animations. And now I'm just going to navigate to the folder that has the Lyra animations that I've moved over into this project. I'm just going to grab everything and put it in. And I'll select that duplicated database now. Now, well, it's idling. It has the idle animation in, but it is switching back and forth between a stop or a pivot a little bit there. If I start moving, you can see it does a pretty good job. It does tend to use the walk start animations sometimes instead of pivots because our character movement component settings more closely match those animations than they do the actual jogging pivot animations. So that's one example. It has a difficult time telling the difference between pivots and stops. Now earlier, you probably saw the character was successfully running at angles, and that's because I was using orientation warping on top of motion matching. I bypassed all of that for this demonstration, so it is just going to try to choose the closest pose here. And now, finally, one of the biggest issues when it's all together is, look what happens when I turn quickly while cycling. The character really just doesn't know what to do. It's going between stop animations, pivot animations, start animations, and it's introducing a lot of foot sliding because there isn't adequate coverage for this kind of tight, slow circling scenario. With more animations, you could definitely get this kind of situation here covered and make it look really good with motion matching. But we're just using the Lyra animations, and so in this instance, we want to just play the cycle loop animations instead of something else. And that is why I've split up my motion databases, so that I can retain some control over which animations get played in which conditions. It's not entirely necessary for every system, but it is beneficial, especially when working with shorter clipped animations, the kinds that you'd be working with in a more traditional character locomotion system. So, let's set up a system like this from scratch in a new project. Okay, here I have a duplicate of the previous project, but I've cleared out the progress that I've made towards having a working motion matching system. Oh, actually, have I? Yes, I have. So we're going to start from something that is quite close to the default third-person template. However, I have migrated the Lyra unarmed animations into this project, and we can see them here. Now, I made a video on my channel a while ago going over the process of migrating animations between projects and assigning them to skeletons that are already inside of the project. Now, I have made a video on the migration process and how we can move animations from one project to another and then assign them to a skeleton that is already in a project and not have duplicate skeletons. It should be linked somewhere on the screen now, and you can definitely give that a watch. I'm not going to cover the process of migrating the animations in this video, but here they are. I've also brought in some retargeted Advanced Locomotion System version 4 leans, though those were just kind of a holdover from the experimental project and I did not end up using them. You could definitely implement them yourself using a similar system to what I describe in my Advanced Character Locomotion tutorial series. I also have these Lyra additive lean animations, which we will be making use of. Now, to begin, you'll need to make sure some plugins are enabled. Under the animation section of the plugin window, you'll want to make sure that you have the animation warping plugin enabled, as well as the motion trajectory plugin and the pose search plugin. The pose search plugin contains all of the nodes you need for motion matching, and the trajectory plugin allows us to give our character a trajectory and evaluate and predict its movement, which is what we'll feed into the motion matching nodes in the animation blueprint. With that done, let's start with some basic character setup. If I play, now I have cleared out some of the logic from the default animation blueprint, so there is not an output pose currently. You can see we can move the character and the character rotates towards our direction of movement. Now that's good in a lot of instances, but the Lyra animations were built for a strafing system, where if we move to the right or left, like we are right now, the character shouldn't be facing towards the direction of movement. The character should be facing forward along with the camera. So to make that change, there are a couple of different ways we can do it, but this time I'm going to click into the character movement component for the third-person character. I'm going to search rotation. I'm going to turn off orient rotation to movement and instead turn on use controller desired rotation. And I have the rotation right here set to a maximum of 270, and that is lowered from the default value in the third-person template. And with that done, we can see that the character rotates to align with the movement. However, if we do rotate the movement too quickly, the character is capped to a maximum rotation speed of 270. And I do think I might increase that to 360 instead. You know what? Let's go up to 500. Let's do 520. I think that would be a good number. I wasn't entirely happy with that in my previous test project, and that feels a bit more realistic, a bit more snappy. So you can, of course, tune these values to what works for you and the animations that you are using to follow along with. Now, with that done, we need to go ahead and add a component that is going to connect to the movement of the character and generate a predicted trajectory. And that is going to be a component type called character trajectory. I'll go ahead and add it to the character, and that's all the setup we need to do for this trajectory component. It does have some settings that we can affect, but I have not needed to change any of these settings for the motion matching setups that I've tried so far. Though, if you get more into the weeds than I have thus far with motion matching, you definitely might find some use in adjusting these settings, and you might be able to find some settings that are more optimal than the defaults, which I'm going to be working with in this video. I'm going to go ahead and compile and save, and now let's take a look at the animation blueprint that we'll be using. I'm going to be building this off of the Mannequin animation blueprint, the Manny, animation blueprint, that is the default one used in the third-person template. The event graph in its current state is what it is when you first open the project. However, I have cleared out some of the logic from the animation graph, leaving the control rig, which handles leg IK, and this default slot for playing back animation montages, though I won't be covering that or using that in this video. So, before we start building out our animation graph, there are some values that we will need to calculate, and we're going to do that in our events graph here. I'm just going to go ahead and add a pin onto the sequence node and calculate the additional values that I'd like to use separately from everything that is here by default. First, I'm going to get the velocity variable that is already here inside of the essential movement data section. And I'm going to multiply it by a new vector that has a value of 1 on the x and 1 on the y axes, with 0 on the z axis. And this is going to clear out any up and down vertical velocity from the character, and this is just a good way to isolate the horizontal plane motion of the character for usage in further calculations related to ground movement character locomotion. I'll go ahead and make this a new variable, which I'm going to name velocity 2D. Next, I'm going to get the character movement component. I'm going to drag out from it, and I'm going to call the get current acceleration function, which returns a vector. And I'm going to promote this vector to a new variable named acceleration. Now, the character movement component has a weird name for this variable, which is called acceleration. It isn't acceleration though, at least not in a physical sense of velocity over time. The way the character movement component moves a character is something like this. It takes in an input vector and it gives it a magnitude that's a result of a function that takes in the max acceleration rate and max acceleration values determined in the settings of the character movement component. This acceleration, each frame is then applied to increase the character's velocity, and the velocity is capped by the max walk speed float variable. So, we can reach a constant velocity, that's our maximum velocity, and acceleration will just be sitting there at some high value that corresponds with the max acceleration. So, this is not a physical acceleration, but it is great for determining what the input is. And a lot of times, we want to think ahead in our animation systems and take action that corresponds with the input before the velocity has caught up to align with the input. So I'm going to take this acceleration and I'm going to do the same thing I did with the velocity. I did not mean to click promote to variable there. I meant to multiply this by a value of 1 on the x and y axes and 0 on the z axis and promote that to a new variable, which is going to be named acceleration 2D. Now I'm going to plug everything in together. Now there are a few more variables we'll need for our locomotion setup. We'll need 2 float variables. And these are going to be called locomotion angle underscore VEL for velocity. I'm going to change this type here to a float. And the second one is going to be named locomotion angle underscore ACCEL for acceleration. And these float values are going to be derived from our 2D velocity and our 2D acceleration respectively. But what is a locomotion angle? Well, it's a useful metric when using locomotion systems and building locomotion systems that corresponds with a angular range of -180 to +180. It describes the direction of the character's movement relative to the facing of the camera along the horizontal plane. So here I'm going to move to the left, and this is going to be a value of -90. If I moved it backwards, -180 or +180. And this is backwards relative to the camera, not relative to the world. If I move forwards, this is 0. If I move right, this is 90. So as we can see, we start at -180, move over to -90. All right, now we're going about -45 up to 0, +45, +90, +135, and finally +180, but that's the same as -180, and it can and does flip between them, especially if you rotate the camera back and forth like this. I'll go ahead and bring both of these variables into the graph, and we can calculate a locomotion angle value quite easily with the function which is named calculate direction. This function is already inside the animation blueprint class, and so we can immediately add it into our graph with no prior setup required. It takes in a vector and a rotator. It asks for velocity, but we can provide acceleration to get a locomotion angle based off of it as well. I'll go ahead and grab both our velocity 2D and acceleration 2D vector variables, and I'll go ahead and get a second calculate direction node here. I'll plug velocity into one and acceleration into the other. And now we need the character's rotation. So I'm going to go ahead and get our character component, drag out from it, and I'm going to get the current rotation with the get actor rotation function. I'll now plug this rotator into both of the calculate direction nodes. I'm not going to worry too much about keeping these graphs clean and tidy in this video, as I don't want it to go on for too long. I'll go ahead and plug both of those calculate direction functions into our variables. Okay, that's going to be it for our event graph setup. For the time being, we have the movement related variables that we need, but we still need a reference to our trajectory. Now, I tried following the pattern. Looks like I accidentally disconnected these, so I'm reconnecting them now. They should be connected already in your case. So I tried following the pattern of casting to the character, swapping this out to the third person character, getting the trajectory component we added, and setting a variable reference, but I just couldn't actually pull the trajectory struct out of that component doing it that way. I'm not entirely sure why that is. To get around that issue, I'm going to open up the content drawer and create a blueprint interface. And I'm going to name it BPI underscore animation data. I'll open it up, and it has a function here that is just a default function that I'm going to name send trajectory. I'm going to give it an input, and it's going to be of the type character trajectory component, and it is going to be an object reference. I'm going to name it trajectory, and I'm going to give it an output as well. It's going to be a Boolean output, and I'll just name that return value. We won't be using this Boolean output in this video, but I do like to add these to my functions within Blueprint interfaces for the following reason, which I'll explain momentarily, but first we need to add it to our animation blueprint. So in this class settings panel here, under the implemented interfaces dropdown, I'm going to search and select our blueprint interface that we've created. I'll compile, and now its functions are added under the interfaces section of the My Blueprints panel. I can click on it, and it takes me to a separate graph for this function specifically. If there wasn't a return value, it would have just created an event in the main event graph, and I prefer to have these functions isolated and separate from everything else, as I like to avoid clutter in my graphs. So that's just personal preference on my part, but that is how I'm doing it for this video. Now I can take this trajectory, drag out from it, and promote it to a variable which I'll name character trajectory. And now we just need to call this function from within our character blueprint and feed in the trajectory as an input. I'll compile and save. And now in our character blueprint, I'm going to get the skeletal mesh. I'm going to drag out from it, and I'm going to get the animation instance of this mesh by calling the getAnimInstance function. And now from this animation instance object reference, I'm going to call our sendTrajectory function. And I'll plug in our character trajectory component. And I've plugged this sendTrajectory node into the chain of functions that are all connected up with begin_play. So this gets sent over when we begin playing and sets the variable locally inside of this function here for our animation instance. Now we can finally begin setting up our animation graph. So I'm going to create two state machines. One for locomotion and one for all movement. So I'll create a second state machine and I'll name it movement. I named the locomotion one locomotion, and I did not mention that as I was typing. From the locomotion state machine, I'm going to save a pose, which I'm going to name locomotion. And this is a super useful node as you can save a pose and then recall it pretty much anywhere else within your graph. So in this case, I'm going to open up the movement state machine, and I'm going to add two states. One which I'm going to name grounded, and one which I'm going to name in air. I'll plug these two into each other, and inside the grounded state, I'm just going to use our locomotion cached pose. And inside of our in air state, I'm just going to grab a fall loop animation. I'll compile. And now for the transition from grounded to in air, I'm just going to grab this isFalling boolean that's already in the Manny animation blueprint from the start, and I'm going to connect it up to the result of the transition. For in air to grounded, I'm going to get the isFalling boolean again, but I'm going to pass it through a not boolean operator and plug that into the result to invert it. And now we can go back and forth from that fall loop to our locomotion pose, which we're saving from the output of our locomotion state machine. So now I'll go ahead and plug movement into this control rig node here and open up the locomotion state machine and add the locomotion states that we'll be using into it. I'm going to add a state which I'm going to name stop, a second state which I'm going to name start, a third which I'm going to name cycle, and a fourth which I'm going to name pivot. We're going to have a transition from entry into stop, and that's because this stop is going to do double duty as an idle and as a stop state. I'm going to create a transition from stop into start, from start into cycle, and then from pivot into cycle. And now there are more transitions that need to occur here into stop and into pivot, but to keep things organized, I'm going to create an alias for both stop and pivoting. And these aliases are kind of like stand-ins for your other states. You can select the ones that apply within the details panel, and then it can transition from any of those states into the state that the alias transitions into. So I can drag and create a transition from the stop alias to stop and from the pivot alias to pivot. And if the condition of the transition rule is met for this alias, then any state we have selected here will transition into pivot using this alias. So I'll go ahead and select just the select all setting for both of these. And we won't get stuck in a loop because an alias cannot enter into itself. So even if stop is selected, it's going to not apply and keep going in and out of the stop state. So that won't be an issue here. The same for pivoting. Next, let's set up our transition rules, and this is where we're going to make use of the calculations that we made in our event graph. From stop to start, we're going to use the should move boolean that is already here by default inside of the mannequin, or Manny, I keep calling it mannequin animation blueprint. And that's just calculated by taking that acceleration, which is input, checking if it is not equal to 0, while also checking if ground speed is greater than 3, and ground speed is just the magnitude of velocity along the x and y axes. So if should move is true, we transition into start. For the stop alias transition, we're going to check if should move is not true. So I'll run it through another not boolean operator. So now, if we should not move, then we go into stop. If we should move, we go from start. If we should move, we should go from stop into start. Once we're in start, we have the option to either go into stop, pivot, or cycle. So let's go ahead and set up that transition into cycle. We're going to get our current ground speed float, and I'm going to get a property access node to reference the character movement component in a thread-safe manner from our animation graph. Inside the property access node, I'll get our character movement component, and I'm going to search for its max walk speed variable. And we're going to check if ground speed is greater than or equal to max walk speed, and plug that into the result for our animation graph. For our transition. And now I'm going to promote this to a shared transition role, which is going to be named cycle. And that way we can assign this shared rule to our transition from pivot into cycle. Now both of these transitions share the same logical rule, and if we change one, the other gets updated automatically to match. Finally, we have the most complicated transition of our state machine, the pivot transition. We are going to compare our 2D velocity to our 2D acceleration. And we're going to check if the direction of our 2D acceleration is opposed to the direction of our 2D velocity. And we can do that quite easily by using the dot product function. I'm going to go ahead and normalize these vectors so that we get to the output in a range of 0 to 1 from the dot product. So I'll run each of these through a normalized node, and I'll get the dot product of the normalized vectors. I'm just going to check if this float is less than 0, and if it is, then the direction of these two vectors, well, on a 360-degree range, they would be at least 90 degrees apart. So I'll go ahead and compile, save, and go back into our state machine. And now we can start filling in our state logic. I'll go ahead and go into the cycle state, and I'm going to create a motion matching node. Okay. Now that we have this node, I'm going to plug it into the output animation pose. I'm going to supply it with a database now, which is not in the project, as we need to create that now. So what we can do is open our content drawer, right click, and go into the animation section, into the motion matching section, and create a motion database. I'll name this one mdb_cycle. I'll open it up, and it requires some assets here that it will need to reference. It has an option for a configuration file, a normalization set, and a preview mesh. I'll go ahead and assign the mannequin as the preview mesh, and I'll create a configuration file asset from the drop-down menu, which I'll place in the same animations folder, and I will name it MDC for motion database config _ Lyra _ unarmed, and I will save it. For this project, I'm just going to use one config that will be shared between all of the motion databases. Now, I'm actually not sure off the top of my head what this normalization set does. I do know it is not required, and I did not take the time to figure it out in my previous experimentation with motion matching, so I'm going to not cover this in this video. Eventually, I do want to make a more conclusive motion matching tutorial once motion matching is out of the experimental phase in the engine, and by then I should definitely know what this does and be able to relay it to you all. Now I'll go ahead and open up our motion database configuration file. It requires a skeleton, which I'll provide it, and it can be given a mirror data table. I'm not going to do that, as we are not going to be mirroring the animations in this system. It has 2 channels by default, and these channels are the metrics that the motion matching uses to compare the character's pose and trajectory to the animation's pose and trajectory. And well, what we see here is that there is a trajectory panel and a pose channel. And that is because we don't have to only compare trajectory and pose. We can compare trajectory or pose or all sorts of other channels. Motion matching can compare any of these metrics here, and they can be a bit, well, complicated. And the crashing legs one is quite useful. It has a good description here, and it's probably the only one that I've used other than trajectory channel or pose channel. These are the 2 main ones, and the crashing legs can help to avoid foot crossing. I didn't bother getting it set up in the previous system, so I'm not going to cover it in this video, but you're welcome to experiment with it yourself, and I encourage that you do. It might give you some warnings if you have it inside the database configuration. At least a friend of mine encountered some warnings, but it still worked properly for him. Motion matching is experimental, so it isn't going to work perfectly and isn't going to be entirely stable yet. I'm going to leave the trajectory channel values at their defaults, and by default, it samples the trajectory 0.4 seconds in the past, and it samples its position. It also checks the trajectory at the current frame and samples the velocity and facing direction for that current frame. It checks it in the future twice, at 0.35 seconds in the future and at 0.7 seconds in the future. And we can see that each of these samples have this flag section, and it's a drop down, and we can choose the metrics of the trajectory point that we're measuring. For now, I'm going to leave these at the default values. Again, I really do encourage you to experiment with these values yourself. It's the best way to gain an understanding of how they affect the motion matching system and motion matching output. Moving on to the pose channel, I'm going to add a bone for it to check, and I'm going to have it check a spine bone, specifically the spine 5 bone. And I'm going to have it track the velocity and position of that bone at a weight of 1. That is something I forgot to mention up here, is that you can provide a weight for each of these points for everything you're sampling and everything you're using in motion matching. You give it a weight, and that determines how much it contributes to the final output pose. And what this spine does, at least what I'm hoping for it to do, is to help stabilize the overall pose and motion of the character. I'll go ahead and save this configuration file and close out of it, and now we can add our animation sequences. There are a few different ways we can do this. We can add one at a time by clicking to add a sequence, clicking into the item, and then selecting the asset. I prefer to just open up the content drawer, navigate over into the file, and search up the assets I want and drag them all in together. I'll go ahead and search mf_unarmed_jog, and I'm going to select the cycle animations, the ones that loop, and not bother with pivots, starts, or stops, as those will be in separate databases. So with the 4 of these selected, I'll bring them in, and we can see that the motion database configuration file tracks whether or not an animation has root motion and whether or not it loops. Now this is important. The root motion helps it to evaluate the trajectory, and if an animation loops, well, you can affect the cost of a looping animation. By default, the cost is reduced by 0.005 for the calculation that determines the output pose, which means it's going to favor looping animations, and you can increase or decrease this cost. I'm going to leave it at the default value. So it will only favor a looping animation if it knows that it loops. It'll only apply that cost change if it knows that it loops. So when you have an animation, you need to make sure that loop is checked. And if root motion is animated, you definitely want to check enable root motion so that it can be processed properly. All right, that's going to be it for our cycle database. I'll close out of it and select it for our motion matching node. Next, I'll get our trajectory by clicking the drop down next to our trajectory in our details panel, getting our character trajectory component, and getting its trajectory struct property. I'll compile and save, and now we've provided the motion matching with 2 of the 3 things it needs. It also needs a pose history, which is not something we supply it with in its details panel. Instead, we need to add a pose history node to our graph, and I'm going to add that here after our locomotion state machine, like that. I'll plug it in, and I'm going to add 3 bones for it to track the pose history of. The 3 same bones that we have established in our motion database configuration file. Foot right, foot left, and spine 5. I'll go ahead and go back into our locomotion state machine. And now we're going to do one more thing in this cycle state. We're going to perform orientation warping using an orientation warping node. And we're going to put this node into graph mode, as this will use the root motion of the animation and automatically determine the offset required for orientation warping to function properly for that animation. Now this is important. You cannot use graph mode if your animations do not have root motion animated and you don't have root motion enabled in the asset to process it. So you'll have to make sure that you have root motion in the animations. You should anyway because you're using motion matching, and you'll need root motion for it to evaluate the trajectory properly as far as I am aware. If you would prefer to use manual mode with motion matching, the best workflow I could think of would be for each of these animations to create a curve that corresponds with the locomotion angle offset required, and then read the curve value at runtime, given the name with a get curve value node, and use that to offset the locomotion angle for orientation warping. And that way, as motion matching switches between different animations, the curve will constantly update. I'll go ahead and get our velocity locomotion angle and plug that into this node. And now we need to give it some settings. I'm not going to go over the orientation warping node in detail here. I did cover it in my advanced character locomotion tutorial series, so I definitely recommend you go reference that for further explanation on how this node works and how to set it up. But all you need to know for this video is that it can change the orientation of the character to extend the coverage. It can rotate the legs and spine so that if we're playing a forward animation, the character's poses could be warped to run at a 45-degree angle instead of straight ahead at a 0-degree angle. And so this is really how the locomotion angle is used and plays into it, is that determines the amount of warping. I'll go ahead and supply it with all 5 spine bones. Spine 1, spine 2, spine 3, spine 4, and finally spine 5. Next, I'll provide it with the IK foot root bone, which is named IK foot root, and both IK feet bones, IK foot left and IK foot right. The control rig that's in this graph by default handles aligning the foot bones with the IK bones that are being moved by the orientation warping node. I'll go ahead and compile, and I'm going to copy all of the nodes inside of this cycle state, and I'm going to paste them into the stop state. But instead of using our velocity-based locomotion angle, I'm going to create a function that'll be bound to the onBecomeRelevant binding of the output animation pose node inside of this state. And it is going to be named setUpStopState. If you're not familiar with how these bound functions work, any animation node in a graph can have functions bound to 3 distinct bindings: on initial update, which is the first time the node is updated; on become relevant, which is when the node first begins contributing to the output pose of the animation graph. What's useful about this binding specifically is that it occurs for 1 frame as the node begins contributing to the output pose, and then it doesn't get called again until the node stops contributing and starts again. So if we switch into the stop state, the moment the output pose here starts contributing to the output pose of our animation graph, the onBecomeRelevant binding gets called. Then it doesn't on the next frame, and if we leave the stop state and enter back into it and begins contributing again for the first time when it didn't contribute on the previous frame, and if it starts contributing again when it did not contribute on the previous frame, the onBecomeRelevant function binding will be called again. So what we can do inside of this function is we can get our locomotion angle for velocity, and we can set a new variable, which is going to be named locomotion angle underscore stop. And this means that we kind of freeze our locomotion angle as we stop providing input for orientation warping in our stop state. I'm going to plug this variable into our orientation warping node. And I'm doing this because the locomotion angle is calculated with velocity. And as velocity moves towards 0, the angle is going to eventually turn to 0 when the velocity vector is 0. And that can cause issues with the orientation warping, as we've stopped, our angle hasn't really changed, we just stopped moving. And so to not confuse the system, we want to set our stop angle each time we start up the stop state and begin transitioning into it. Next, we need a new motion database. So I'm going to duplicate the cycle database, and I'm going to rename it to ndb underscore stop. I'll click into it. I'll clear out the jog cycle animations, and I'll navigate into our animations folder and search mf underscore unarmed to ampersands and stop to search for animations that contain both of these, and I'll actually go ahead and do that again for jog. This will isolate the 4 animations we need. I'll drag them in and save. That's going to be it for our stop state initial setup. Moving on to the start state, I'm going to paste what we copied from the cycle state, leave the velocity locomotion angle in, and just create a new motion database for starts. I'll copy the stop database or the cycle database. It doesn't really matter. I'll rename it to mdb underscore start and swap the animations for the start animations instead of the stop or cycle animations. Back in our animation blueprint, I'll select the start database. Finally, we have our pivot state. I'll go ahead and paste what we've copied and create a new motion database one more time. I'll copy one of the existing ones, rename it to mdb underscore pivot, and put in our 4 jogging pivot animations, while removing the previous animations that were in the database. There is one thing I did forget. We need to go back into the stop database and add the idle animation in. I forgot to do that. This is because, again, our stop state is pulling double duty as an idle state as well. Okay. Back in our animation state for pivoting, I'll swap the database to the new pivot database. Now, we need to change up how we apply orientation warping for pivots. Our pivots actually start going in one direction and then switch to another. If we use velocity, our velocity will do a 180-degree shift, and it's going to move towards 0, and that's going to make the locomotion angle think that we're rotating towards moving forward and then rotating the other way. It's not a super accurate measure for single axis switches in direction. And so what we need to do is start out by using our acceleration locomotion angle and then swap to our velocity. And so we are going to do that corresponding to the point in the pivot animation where we switch from moving one direction to moving the other. I'm going to click on the output animation pose node, and I'm going to add a function bound to its onUpdate binding, and this will get called every time the animation node this is bound to is updated. And I am going to name this update pivot state. And inside of here, I'm going to get our acceleration and our velocity locomotion angle, and I am going to get a select node. I'm also going to create a new float variable, which is going to be named locomotion angle underscore pivot. I'll pull that in, plug it in between the entry and return nodes for the function. I'll plug the result of the select node into the set node for the new variable. And now I'm going to get the logic for our transition into the pivot state. I'll select everything that's in here, go back into our update function and paste it. And so we're going to take the resulting Boolean of this calculation and plug it into the select node. So if our velocity and acceleration are in opposition, we're going to use our acceleration locomotion angle. We'll plug that into the true. If they're aligned, we'll use velocity. And this will switch at the right moment to ensure that our legs do not swizzle around with the orientation warping while pivoting. So now we'll plug the pivot locomotion angle into the orientation warping node. And finally, well, let's just go ahead and check and see what things look like now that we have motion matching in each of these states. We're not done with our setup. We're definitely not done because it looks like we're in the cycle state. I may have made a mistake. But I do want to see, well, what things look like thus far and check for those sorts of mistakes, which we have one. I did not change the stop states motion matching node so that it would use the stop database, and it was still using the cycle database. So now that's better. The transitions do not look great, and the next steps that I'm going to take are going to address the transitions directly. This is not going to make the transitions look perfect. The transitions are always the most difficult part of most animation systems to get looking right when using multiple states and switching between them. So you may want to invest more time to fine-tune things yourselves, but I am going to do the following. I'm going to change the transition rule for every single transition to be inertialized. And I'm going to add an inertialization node after our pose history node. And instead of using a normal inertialization node, I'm going to use a new type of node that's new to 5.3 called dead blending. And it does the same thing as the inertialization node, which allows us to use inertialized blends. It's just better and doesn't have the pose popping issues that the old inertialization node had. And an inertialized blend is just a blend that takes into account velocity along with position, instead of just position like the standard blend does. Let's see what it looks like with inertialization. I do think it looks better now. There are still some issues in the transitions, but I believe these are all due to the root not being at the right starting point in some of the animations. And this is going to cause the pelvis's location relative to the root, which is always going to be constant and tied to the capsule, to change. And so the pelvis is going to be forcibly moved to align with the root, the way that it does in the animation. And that is causing the foot sliding during the transitions. And there isn't anything I can do about it without modifying the Lyra animations and cleaning them up further. And that is not the focus of this video. However, a friend of mine, Ryan, the creator of the Animation Matching Suite plugin on the Unreal Engine Marketplace, a super useful plugin that I either already have or will be making a video on very soon, depending on when this video goes up. Well, recently he's created a new sample project for his plugin, and inside of it he's extended the Lyra unarmed animations to cover 8 directions, and he's fixed the root animation issues in the animations. So I think the plugin is worth the price alone just for that project and those animations and the cleanup that he's done there. But you get a suite of super useful tools along with it. So definitely check that out. I highly recommend it. Moving on, I believe this is going to be it for our motion matching setup. And now we're just going to do one final thing, and that is to perform some additive leans. I've brought in the additive jog lean animations from the Lyra starter project, and these animations are animated where the character is holding a rifle. This isn't an issue though, because they're additive, and they're going to be relative to the center pose, where the character is also holding a rifle. So the difference between these is going to be the rotation and not any sort of change in the posing of the arms, which will allow us to use them anywhere. To apply these, I'm going to create a new animation layer, and I'm going to name this layer Lean. I'll give it an input. And inside of here, I'm going to search mesh space and choose the apply mesh space additive option to get that node. I'm going to create a new 1D blend space graph inside of this graph here. I'll name it lean additive. For the name of the horizontal axis, I'm just going to name it lean amount. The minimum value will be -1 and the maximum will be 1. I'll go ahead and search for the lean additive animations, and I'll get the left one and put it on the left, and the right one and put it on the right. Now, if I look at one of the animations, either the right or the left, we can see how I've set things up. Each is additive in mesh space and is local to the first frame of the jog lean center animation. And these settings need to be set this way if you are using an apply mesh space additive node like I am. I'll plug that into the additive value. And now we need to calculate the alpha. We don't want to apply the lean when we're not moving. So I'm going to get the ground speed float. And I'm going to get another property access node, get the character movement component, and get the max walk speed variable. I'm now going to divide ground speed by max walk speed with a safe divide node, which returns 0 when the input for the divisor is 0. So now we'll approach an alpha of 1 as ground speed accelerates to match our maximum speed. And as we slow down towards a speed of 0, the alpha slows down or lowers towards 0. Next, we need to calculate our lean amount. And we are going to do that by creating a few more variables to work with in our event graph. So after we set our locomotion angles, I'm going to get the character as actor rotation again. And this time, I'm going to break the rotator and just use the yaw. I'm going to set a new variable, which is just going to be named yaw for simplicity's sake. And I'm going to duplicate this variable and name the duplicate previous yaw. What I'm then going to do is set previous yaw before we set yaw, and I'll set previous yaw with the value of yaw. So every frame, we take yaw, we use it to set previous yaw, then we update yaw. So this will track the yaw of the previous frame. And now we can subtract the previous yaw from our yaw variable to get the delta between the two, the change in yaw for each frame. And I'll promote this to a new variable, which I will name yaw delta. I'll plug it in to the string of nodes here, go back into our lean layer, and now I'll plug our yaw delta in to our lean amount. Okay, now that the yaw is plugged in, I'll go into the animation graph, and after our dead blending node, I'll go ahead and add that lean layer in. Now we have not finished the lean layer, but I want to demonstrate the issue that we're going to encounter if we just use the yaw delta directly. We do lean, but it is an instantaneous lean. And if I walk backwards, we lean in the incorrect angle. To fix this, the simplest approach, it does have a trade-off, but it is the one I'm going to use. And it is to go into the lean layer. I'm going to get our yaw delta, and I'm going to multiply it by the result of running our velocity-based locomotion angle through a map range clamped node. It's going to be the input value, and range A is going to be 180, and range B is going to be 0. Out range A is going to be -1, and out range B is going to be 1, and I did make a mistake. We need to get the absolute value. So now, as we move from forwards towards backwards, we kind of invert our yaw delta. It does remove leaning when we strafe, but it is simpler than setting up a direction enumeration to track and use to determine what we should be multiplying our locomotion angle by. Now, this approach does get rid of any sort of lean when strafing from left to right. I'm implementing the fix this way for this video because I've been recording for quite a while, and I don't want this video to be too long. One option that you could pursue, if you wish, would be to add a curve to each of your animations that you're using in the system with a value of 1 or -1 to determine which way the character should lean when moving. In the animation where your hips are facing backwards into movement, such as the backwards or left strafing animations in Lyra, you'd want to multiply by -1, and any animation where the character's hips are facing forward into motion, you'll want to multiply by +1. So you put -1 or +1 into a curve, they all share the same name, and each animation has the curve, then you multiply yaw delta by that. Finally, inside of the lean additive, I'll set the wait speed for our sample smoothing to 3 and the allow mesh space blending boolean to true. And now our turning is smoothed and it does get applied. All right, everyone, I'm going to end the video out here. Thank you so much for watching. I hope you found this video useful. I plan to do more comprehensive motion matching tutorials in the future. I want to give a special thanks to all of my Patreons over on patreon.com/OutcastDevSchool for their continued support of the channel. You can get the full project files for this video on my Patreon, as well as the project files for other tutorials that I do for $10 a month. Thanks again for watching, and I'll see you in the next video.